So, how would you define what an isotope is or what isotopes are? What are isotopes?
Same number of protons, different number of neutrons.
Very good. So Megan says same number of protons, different number of neutrons. You should put in there what? Elements, right? Same proton means the same element, right? That's what we said the other day. The proton is the signature. If I say 6 protons, it means it's carbon, no exceptions. If I say carbon, it means 6 protons, no exceptions. On your periodic table here, it's the number above the element symbol, right? That's the number of protons. So atoms of the same element with the same number of protons, but different number of neutrons. So one thing I said the other day too is the number of neutrons can vary, the number of electrons can vary. It's still going to be the same element. The number of protons varies, then you're talking about different elements. And a nuclide is just a specific isotope of an element. So we use a notation to show what a nuclide is, and we'll do that today. So that's just the terminology for a particular isotope that we're talking about. So here's the terminology we use, or the symbol we use. Of course, there's no element X, that's just a placeholder here. And A and Z are placeholders. So X would be your element. Z is the nuclear charge or the atomic number. And then A is the number, the atomic mass. That's wrong. It's not really the atomic mass because it's not an atomic mass unit. It's a mass number. And A is basically equal to the number of protons plus the number of neutrons. Okay? So you can easily figure out the number of neutrons, right? By say taking A minus Z. And I think that's the only formula I have on the outline sheet. It's not really, I don't consider that math. That's just, it is math, but it's obviously not college math. You learn that in whatever, I don't know. When do you first do addition and subtraction? Sometime in elementary school, but I don't know what year. So that's a simple way that we can notate a particular nuclide. Now, some people use a shorthand notation too, and I'll show you. So most elements have 2 or more isotopes. And I can never remember. There's like 1 or 2 elements, I think, that only have 1 isotope. Some have oodles of isotopes, like a bunch, 16 isotopes. I mean, you can look, there's charts of all the different known isotopes and things like that. That's just the definition of isotope again. So here's 2 isotopes of neon right here. So neon 22 and neon 20. So you can see, obviously, they have the same number of protons because that's the atomic number. And the top number varies by the number of neutrons, and we can just subtract it, and that's all it is. So some people will do things like this. And why is that okay to do that rather than having the 10 there? Yeah.
Because you know how many protons are going to be.
Right. We know how many protons are going to be there, so it's kind of redundant to say 10 and neon. So you'll often just see it written like this. You might see carbon 14, which is kind of a famous isotope, right? It's one of those ones we can use for dating. So if something was once living, we can use carbon 14 for dating, and that is because carbon 14 is radioactive. Okay, we've defined radioactivity now. You have a sense of what it is. It means that nucleus is unstable and it's decaying over time. And these things are so consistent with their decay rate that that's how world time is set. World time is set with cobalt 60, I believe it is. It radioactively decays at such a consistent interval. That's how we set world time. Everything is based off of that. So they're not subject to environmental conditions for the most part. There are some weird exceptions to that. And that's because this is a nuclear process, right? Radioactive decay is taking place in the nucleus. So I can't speed up reactions, nuclear reactions, by heating things up. We'll learn that over the course of Gen Chem 1 and 2. When you get to Gen Chem 2, we'll talk about kinetics and things like that, which is just a fancy word for rates of reactions. That has to deal with chemistry. Chemistry deals with what's going on outside of the nucleus, the electrons. When you think about bonding and chemical reactions, you're dealing with a nucleus like this, a bunch of electron shells we'll learn about in chapter 3. And if two atoms come together, what's going to interact is these two outer ones, right? If here's another element here, it's the electrons. That's where all the exchange is going on. Electrons are being shared. Electrons are being given off, right? Taken up. Bonding takes place with the electrons. So when we talk about the nucleus, it's really physics. That's one of those areas that both chemistry and physics overlap. We call it nuclear chemistry. We have a whole chapter in our book called Nuclear Chemistry, but the nucleus really is physics work. And the stuff we're going to do in chapter 3 is, most of those guys were all physicists. All the quantum theory stuff, electrons and all of that. And when you look at Ernest Rutherford, he considered himself a physicist, not a chemist. But of course, we need to cover that. It should be complete. So some isotopes can be radioactive, and we can use that radioactivity as a way to do something. We can date something because it's so consistent. Let's practice here. Write nuclide symbols for the following nuclides that have A, 6 protons and 7 neutrons, and then another one, B, 95 protons and 146 neutrons. And do that real quick. Raise your hand if you got one and you want to share it with us. Second one, go ahead. 243? 241, right? 241, 6, yeah. Bottom number? 95. Americium 241. Very good. Okay. All you have to do is take the 146 and add it to the 95. You get 241, and then the 95 is the number of protons. So that's that isotope. Every one of you, more likely than not, has that isotope in your house. It's used in smoke detectors. It's radioactive. So basically, the smoke will interfere with the radioactive signal. That's the radioactive keeps that light on. It keeps that sensor going. The decay, basically, the alpha particles and gamma rays and things like that are just keeping that signal until the smoke interferes with it, and that's what triggers the. Some of them work on heat too. Interferes with it, and then you get a alarm sound. And the other one is what? Carbon 13. Very good. Okay. Question. You can fill this out at home. I mean, what you've got here now, I want to point out, I'm not going to fill out the whole thing. Let's just do this first row. We got sodium 23. What's the atomic number going to be? 11, right? Mass number That's just the 23. Number of protons. Number of neutrons. Number of electrons. 11 also, right? Because it's neutral. All your atoms are neutral. You just talking about an element on the periodic table, it's neutral, so the number of protons has to be equal to the number of electrons. Okay? If not, there'll be a charge there. So I would do something like this. If it wasn't the element and it was an ion, I'd ask you, okay, sodium plus, and we don't put the 1 there. 1s are just understood. Sodium plus, now you have 10 electrons because you've lost an electron. What has happened as sodium has gone like this, the sodium plus 1 electron. It's given off an electron. So you say it's given off, so how's it plus? Well, it's just like algebra. 0 equals a 1 plus a negative 1, if you will, right? Electron is negatively charged. Okay. Take chlorine. Chlorine likes to gain an electron. We're going to wind up with this. 0 plus a negative 1 equals negative 1. Electron is negative, so it picks up a negative and becomes negative 1. So if you see a charge in the right-hand corner, then your numbers of electrons might be different. This table, there are no charges. So in other words, you can't do it, right? You wouldn't know if, like for this one of these, for the second one, they don't tell you whether either that or that, so you can't do it. None of these have charges. But sometimes, that says ions over there, sometimes you need to know, sometimes you'll be asked this, so you need to know how to do it. Ions, that was just a note for me to talk about that. Does that make sense? What ions are? Okay, ions are atoms that have gained or lost electrons. Cations are positively charged, anions are negatively charged. Okay, and they're going to be the building blocks for your ionic compounds or crystals. Sodium chloride being the classic one. You can see now the sodium attracts chlorine. Silence my phone, apologies. You can see that sodium will attract chlorine very easily because they have opposite charges, and that's what makes up sodium chloride, salt, that you know is table salt. Okay, so everybody comfortable with being able to do the other 2 columns at home? All right. Periodic table. So Mendeleev gets the credit. There was another guy working at the same time. I always forget his name because he's the one that always given the credit. And basically, he just published his first. They were kind of doing the same stuff. But he ordered elements. Let's see the way they've got it written here. Yes, okay. So in Mendeleev's periodic table, elements are ordered by increasing atomic mass. Okay. Atomic mass is the number at the bottom on your periodic table there. It's not shown here. That's different than mass number. Mass number is simply protons plus neutrons. Atomic mass is an actual mass, okay? Because a proton and neutron don't weigh exactly 1. Okay, we saw on a table, what was earlier, it was Tuesday, right? The actual mass right here. Here's the actual masses of protons and neutrons in kilograms, and then atomic mass units. When we do things like atomic mass units, that's just for convenience. So we don't have to write 1.67493 times 10 to the minus 27. Okay? It's just a normal, we call that normalizing data. Just simplifies things. We do that with pH scale. You'll see that in Gen Chem 2. And you can see to 3 significant figures, 1.01, neutrons and protons are exactly the same. The atomic mass then is the number at the bottom of this periodic table up here. And that's how he arranged them. And what he did when he got to an element, so he would put them across from each other, increasing atomic mass, right? And then when he got to one that was similar to one that he already had, instead of keeping going across, he put it underneath that one. His idea was, let's group ones that behave similarly. And that means that, hey, he noticed, maybe that I'm just making this up. I don't know exactly what he noticed. Let's pretend like he noticed that, hey, sodium forms with chlorine in the same ratios, kind of like as potassium and chlorine, and they both form this chloride salt. So I'm going to put it underneath each other. Okay, they have maybe some other similar properties in appearance, something like that. So he grouped them together. So as you're seeing on the periodic table is elements that are in the same group will have similar characteristics. They can, form similar compounds. They can have some other physical and chemical characteristics that are the same. Doesn't mean they're, the same in every aspect. They're different also, of course. They have different numbers of electrons. He left spaces where he figured there should be an element here. And quite frankly, what I do remember about this is, heck, I thought it was. Well, who knows who knows? I don't know with this table. I could have sworn silicon was one he left a blank for, but anyway, he left blanks where he predicted there to be elements. So I must be mistaken about silicon. Anyway, maybe it was under silicon, I was thinking. So he left blanks in the way he arranged it. And of course, then his arrangement was quite different than what we have today in terms of having transition metals and all of that, because we've learned a lot more about things. But sure enough, later on, elements would be discovered, right, where you had a question mark and would fit right in. And even in some cases predicted, like, I think the density is going to be around this, because he knows, hey, as I go down, the density gets greater. So he would predict this density. He'd even predict, like in some cases, it's kind of lusters, things like that. It'd be pretty accurate. Well, now we know that they should be arranged in order of what? Not atomic mass, increasing atomic mass, but what? Atomic number, right? Because that's the signature. An atomic number is equivalent to the number of electrons, and that's what gives you those chemical characteristics. How many electrons it has, what it's reacting with on the outside, right? So the atomic mass is really not that important. It's the number of protons, which leads to the number of electrons. And there are a couple of cases where you'll see a switch, and we have to look up here to find them. I can usually find one or two pretty quickly. There's one over here where right here, tellurium and iodine. Oops, sorry. Let me just put this. Tellurium and iodine. Iodine actually has a lower atomic mass than tellurium. Okay, but we got to have this one to the right because it's got a greater atomic number. So how can you have a lower atomic mass if you've got, right? Well, it comes down to what the definition really of atomic mass is. What is it? No, that's the mass number. What is the atomic mass of an element? Very good. Bingo. Average mass of all the isotopes. So that means that is that there's some isotopes of tellurium that are heavier so that it makes the average mass greater, even though iodine has more protons. That's all it means. Okay. So when you add up all those isotopes, you wind up with an average mass. And that's if I had a box of balls up here, all different balls, and then ping pong balls and bowling balls, and I asked you for the average mass, it's no different. That's all that is up there. Because think about carbon. You got carbon 13 we just did. We know carbon 12, that's the main one, 6 protons, 6 neutrons. And then carbon 14 I just told you about. So when you get an average up there, it's slightly over 12. Which, if you're thinking, can trigger you to realize what the major isotope of carbon is. What is it? Right? 12, right? Because the mass is so close to 12. Now, you could have said, well, Dr. D, maybe there's carbon 8 or something like that, and it's just averaging out to 12. And that's true. It's perfectly valid. But in a lot of cases, the major isotope is the one that's super close to that atomic mass. Okay? And that's because a proton weighs roughly 1 and a neutron weighs roughly 1. And there's carbon 11, but it's really rare. Carbon 12 is by far the major isotope. Yes. I don't know. I have no idea. I'm not sure if it's used for anything. Some of these isotopes have really short half-lives, and therefore we've identified them, but they're not usable for anything. But carbon 11, I have no idea. So many isotopes, it's, tough to keep track of. All right, so here's our modern periodic table then. Increasing atomic number, similar chemical and physical properties in columns. We got our break here now, and this is done for really convenience. And putting these, I'm sorry, this down here is done really for convenience. So if you really would have to break the table all the way right here, separate 21 and 22, push this all the way out, and then you'd have the whole gap there. These also are grouped for certain reasons, also beyond convenience. So, but it's nice. This fits on an 8.5 by 11 piece of paper. And I've got, a slew of them in my office that all fit nicely on a page. So, we've got metals, non-metals, metalloids. The metals are your bone color, I guess we call that. The non-metals are blue. The metalloids are green. When you think of metals, what do you think of? Characteristics of a metal. Shiny, not always, but that's some of them. What else? What's that? Conduct heat. Malleable, ductile, conduct electricity, of course, right? These are all characteristics of metals. Non-metals are the opposite for the most part, and metalloids are somewhat in between. They conduct electricity, but not as good as metals, and so forth. That's where you find your semiconductors, or it's semiconductors, partial conductors, really. Of course, silicon is hugely important. It's what all our integrated circuits are made of, so silicon is a hugely important element. Some of the metals on the right over here aren't as shiny as some of the others. Some of them are cut up. You can cut with like a butter knife. They're kind of a softer metal. There's only 2 liquids on the entire periodic table. When I say liquids, of course, I mean at room temperature, because I can turn anything into a liquid. I can turn anything into a gas. So what are the 2 liquids? Mercury and bromine. Very good. There's your 2 liquids. So you go down the periodic table, you've got gas, liquid, solid. It becomes denser and denser. Bonding changes, we'll learn about that. Of course, these are your noble gases. These guys, nitrogen and oxygen, are also gas. Hydrogen's an oddball. He's a little bit schizophrenic. So he's kind of like, he's in group 1, but he's a gas. I hate he, it could be a she. I don't know if hydrogen's male or female. So he hangs out over there. And for certain reasons, we'll learn, because we'll see charges. We're going to do that right here. Hydrogen's +1, like other group 1. But it's a non-metal, so we want to put it over here. But it's +1, we want it over there. So sometimes you'll see some weird periodic tables with hydrogens kind of floating out here. I don't think they're very common, but I have seen those. And there's some other things you'll learn about. Why hydrogen's kind of like a little schizophrenic. But those are the common charges you see for elements. When I say common, what I mean by that is these are charges that these elements will form in chemical reactions, or they'll be, if they're present in water, this is the charge they'll have, you know, dissolved in water, that type of thing. So you notice group 1 is +1. And group 2 is +2, and that's pretty exclusive group. You're not going to see anything but +1 and +2 there. When you get to the right side, they're a little bit more finicky and they can take on different charges. This doesn't show you that, but chlorine can be a lot of different things, but these are the common ones. That's the nature of this chart. So group 17 is -1, group 16 is -2, group 15 is -3, group 13 is +3. Then you got your transition metals. You'll see a lot of 1s and 2s in there. But you get some 3s, you get a +6, they don't even show. Chromium, kind of important one, 6+. That's the one that is pretty toxic, carcinogenic compounds. That's the one, if you ever know the Aaron Brockovich story. That's the, one of those environmental stories. If you don't know the story, you can watch the movie. There was a movie made with Julia Roberts starred as Aaron Brockovich. But basically, it's chromium-6 was being used by, I think it was DuPont, to, I think they were using it as some sort of degreasing solvent or something like that, or anyway, in their water, or descaling agent in their water towers or something like that. It was leaching into the groundwater. And she's one of the moms that lived there that became active, similar to, I think it was Lois Gibbs, the Love Canal story. I talk about a lot of the stuff in my environmental class, but chromium-6 is pretty bad. And she's the one that kind of brought attention to it. And, got the government involved and forced, clean up. People were getting sick on this stuff. It was getting into their drinking water. Questions? Yes.
What is monatomic?
A single atom. Okay, so mono, atomic, single atom. So it's, I guess it says up there, common charges on monoatomic atom. As opposed to, good question, as opposed to something like this. This is a polyatomic ion, more than one atom. We'll learn about these. You'll have to kind of kind of not commit to memory because everything's open book, open note, but learn some of these polyatomic ions and recognize them. I think that comes up in chapter, I thought it was chapter 2, actually. Anyway, so here's some group names you should get familiar with. Now, one thing I won't ask you is what's the name of the elements in group 1, because it's right there in your book and in your slides. I might ask you something different, might give you a couple elements and ask you something about them just to make sure that you're getting familiar with the periodic table. Alkali metals, alkaline earth metals, halogens, noble gases. I never learned the chalcogens, but now they use that term also for group 16. We good? Okay, so here's neon. I showed you 2 of them, but now there's actually 3 natural isotopes of neon. And here they are with the mass in atomic mass units and their abundances. And it's fairly common to have one isotope that's far more abundant than the others. Not always. Okay, chlorine's pretty evenly split between 2 isotopes. But that's pretty common to see that where you've got one isotope that dominates, has like 90% or more. And that's the case for carbon. The average atomic mass is calculated. So, what's your name? What is it?
Houston.
Houston said this number, the atomic mass, is the average of all the isotopes. Let's see where it comes from. Neon is 20.1797. This is where that number comes from, right here. Let's do it. Okay, so if I told you I had a box of balls up in the front of the room here, and I had 3 types of balls, and they had these 3 different masses, and I told you the percentages, could you tell me the average mass of a ball in that box without knowing the numbers? You're shaking your head yes, right? You don't need to know the numbers, right? I don't have to tell you there's 50 balls in there or 65 balls, doesn't matter. You've got the percentages, right? You can convince yourself of this by doing an average and just listing 10 numbers or doing it as a percent. So we don't need to know the numbers. We can just do it like this. Take the mass times the percentage. So there's neon 20 right there, right? There's its mass times its percentage in fractional form. We're going to divide by 100. We can't use percentages in our math. Second isotope with its percentage, just move the decimal place over twice because we're dividing by 100. And the third one times its percentage. That gives you the answer. You don't need to know the numbers of objects, whether it be atoms or balls or whatever, it doesn't matter. If I said to you, I've got, let's see. No, that's all right. The bowl analogy is fine. Does everybody see how this is done? Is there questions about this? You see the number now. It's 20.1799. 20.1797 is what that periodic table has. So we'd have to see whose number is better. Someone probably rounded off something differently or something, or maybe we've got additional information on isotope abundance since these periodic tables were made. This is a brand new edition of your book, so this is probably more reliable than that periodic table. Questions? So I'm not going to ask you a question like this on the exam because you can just look at the periodic table and not answer and not do the math. What I will ask you is the reverse. I'll tell you there's 3 isotopes. One is this percentage. One is this percentage. And there's a third one. What is its mass? That's what I'll ask you. Right? So you now have this number here, right? And you have this number and this number, and you have this number and this number. You can get this number by subtracting 100, right? If I tell you it has 3 isotopes and I tell you the abundance of 2 of them, I have to add up to 100, right? So if I do 100 minus 90.483 minus 0.2696, I'll have this abundance here because I have 2 unknowns, right? I need 2 equations. I've got 2 unknowns. We'll do one of these. I know a lot of you are looking at me like I'm insane. Some of you are right on top of it, which is fine. But and then you can solve for this, and then you got to do the math. You'll be solving for, what did I ask? Neon 22, which is this one right here. That's what you'll be solving for, that number right there. So you'd have to subtract this, and then divide by this to get this, right? And now you have this one right here. So practice that. Pretend that's the question. You have all the information. Solve for this right here. Pretending you already have this here and solve it. You've got the answer. You know you better come up with this. You don't have to do it right now. You can do this at home. We're going to do one right here with silver. Okay, but then this is how you practice. You take the example I gave you and solve it backwards. If you do it multiple times and get it right, then you know you're ready. So here's one. Silver has 2 stable isotopes. Silver 107, that's its mass number. You notice the atomic mass is actually slightly different. That's why I said to you, that's why I made that correction on the one slide. And silver 109. This one's even harder because I've given you no percentages. Okay, this is the one from your book, sample exercise 2.5. We have the atomic mass, that's straight from the periodic table, but now we have no abundances. So how do I solve that? How am I going to solve this? I don't have the abundance of either one. But there's only two, right? So what do? If there's three, forget it. What do you do? X and what? Yes, very good. X and 1 minus X. Right? We know the total has to be 100. And in fractional form, the total has to be 1, right? Because we're dividing everything by 100 to use decimals. And if there's only two of them, we'll make one of them X. And let's say it's 55%, just assume. The other one has to be 45%, right? 1 minus 0.55 will get you 0.45. Very good. So that's how you got to solve it mathematically. We know the masses of both isotopes of silver and its average atomic mass. We're asked to calculate the natural abundance of each. We know there's only two there. They add up to 100%. In this case, the weighted average is 107.87. That's from the periodic table. And we're just thinking about it now. About halfway between, right? Think about it's what the coast thing of think about your answer. In this case, you don't have the answer yet. Think about what you're doing. It's 107.87, almost 107.9. So they should be pretty close, your answer, to 50% and 50%. Right? If the average mass was 108.8, we know that most of it's going to be the heavier isotope, right? That's what I want you to think about. You're going to see that type of question right after this and on the exam. But think about it logically without any calculation. So let's finish this one, and that's what's coming up next. So, what's your name? What is it? With an H? Okay. I wasn't sure if you said H or K. Hersha. So we're going to do exactly what Hersha said is, here we go. This is the periodic table number, okay? And this is the 107. It doesn't matter which one you call X and which one you call 1 minus X, right? Doesn't matter. You just got to remember which one you assign. So when you get your answer for X, you know which one that is. In this case, they're doing, and I've just taken this straight from the slides the publisher gave me. So they're doing X is the 107. And this is what we did before, remember? This would have been a percentage here before. It would have been 0.69 if it was 69%. Now we're just putting X there because we don't know it. And now we're putting 1 minus X here. And we're multiplying it by the same thing we did here. Same thing. Just that you're working a little bit backwards. You take the mass and multiply it by the percentage in fractional form. So my X and 1 minus X are going to be my percentages in fractional form. And then you got to be able to solve that. Okay? I'm not going to teach you algebra. You're supposed to know algebra coming in. So you have to go home and make sure you're comfortable solving this. And you should get X is 0.5050. That means 1 minus X is equal to 0.4950. And remembering that we assigned X to be the 107 times 100, that gives us 50.5 and 49.5, kind of what we predicted, about a 50-50 split is what we would expect because that mass is almost exactly in between. Questions? Trust me, if you're not following this, there's a lot of you. I know, I've taught this enough to know that when I get a question like this on the board, I'm lucky if 20% of the people get the correct answer. So that means that about 80% of you probably have got some sort of discomfort with what we just did.
I assume on the exam that all the equations we're going over, we're gonna need to know by memory, right?
This is, I don't think of this as an equation. It's the mathematical algebra needed to solve it. So yes, there's nothing giving to you here other than what you see here. That's it.
Says the average atomic mass is 107.87,
Uh-huh.
but when you set it up, it was 107.89.
Oh, I mean, well, I didn't make it. They did. This is straight from the public. Yes, very good eye. Attention to detail. Yeah, this should have been, and you can double check that. It probably won't affect the answer, but double check it when you get a chance. It does. So what do you get?
48.5%.
Oh, really? So when this is actually a 7, you're saying here, it affects it that much. And you get what?
48.5%. 51.5%.
Very good. And I'll double check to make sure the 107.87 is correct, and maybe they had that wrong in the original problem. But very good on. Regardless, the important thing is you know how to do it, right? Or you don't, you're going to learn how to do it if you don't know right now. Questions?
There are plenty more questions like this in the book.
I know assign something in the back. There's I can't remember if I have one on smart work or not. If it was there, I probably assigned it. So yeah, there should be a couple. And to be honest with you, you can take these and do multiple problems from them. You can now, not for this one, but the neon one we did. This one's ideal where you can actually do it for each of those 3 isotopes and just get comfortable doing it and make sure you get that answer each time. You got the answers right there now. You're solving for this or the abundances. Okay, now this is what I meant by thinking about it logically with no math. The 2 major isotopes of bromine are 79 and 81. Okay, so it's, a little bit odd, and then you think that, well, there's 79, 80. What happened to 80? Well, it's just not that abundant. Assume that the masses of 79 and 81 are 79 and 81 exactly to 4 sig figs. The weighted average is 79.9. Okay. What are the relative abundances of each isotope without detailed calculation? So which one of those answers is the only one that makes sense based on the information you're given? B as in boy, D as in dog. Very good. How'd she do that?
Less than 80, you know that the one with the less mass is.
Bingo. Exactly what he said. What's your name?
Parker.
Parker. They're roughly 50%, right? Because the 79.9 is almost 80, and that's right in between. So they're going to be close to 50%. So really, this is the only one. Even if one of these was closer, a better question would have been if you had those almost had these almost switched and had 55 and 45, And then Parker's final reasoning was that it's closer to the 79, right? So 79 has to be more than the 80. What was your name? Did I ask you? What's your name? What is it? Sonia? So Sonia, this is what her thinking was, and Parker explained it. You have to know that this one, excuse me, is going to be more based on that number, and therefore that's the correct answer. So a tougher question is if I had 55 and 45 switched right here. You know it's not these two. They're not close enough to 50, and even the 60-30 one is not particularly close. Questions? All right. Molar mass. I'm not going to spend much time on this, or molecular mass, actually. Molecular mass, because this is just adding up the masses from the periodic table. So what you see there is AMUs. I can add them all up. 1 sulfur, 2 oxygens. And they're doing it by dimensional analysis, but I don't do this. I take out my calculator and go 32.065 plus 2 times 15.99. Okay, you don't need to really set it up like this. You just add up the numbers. That's what molecular mass is. And the units are AMUs. When you're pulling them straight from the periodic table, they're AMUs. Questions? So if you have something, outside the parentheses also, that means everything inside the parentheses is multiplied. So if you had something like this, you would have to have 12 hydrogens, right? And 3 nitrogen when you do all your adding up. Okay? Any numbers outside, it's kind of like algebra, almost like a number out in front of parentheses. That's molecular mass. Formula mass. Now, this always annoys me. I wish they would just call everything a formula mass. And we call this a formula mass because calcium chloride is an ionic compound, and there are no molecules. So molecular mass doesn't make sense. I wish they'd just call everything a formula mass. This would be a formula mass. So formula mass is used for ionic compounds. Molecular masses is used for molecular compounds. So if it has a metal in it, the left side of the periodic table, we call it a formula mass. There's nothing different to do. It's still the same units, so you still just add them up. There's nothing different to do. So once again, I don't do it like this. I just go calcium plus 2 chlorine, done. Okay? I do want you to recognize that there is no such thing as a molecule. It's important for an ionic compound. Okay? They have crystals. Okay? And you can't get a single stable NaCl or CaCl2. You'll have a bunch of hundreds, probably thousands before you get an unstable crystal of atoms grouped together. Okay, everybody's dreaded mole. I don't know why. It's really not that bad. All right, so I want you to imagine a periodic table. In my periodic table, there's going to be a bunch of different types of balls. Golf balls. I try to hit one once in a while. Baseballs. I'm a big baseball fan. I'm not going to put a hockey puck in there, even though I love hockey, because it's not really a ball. I'm not a basketball fan, but we'll put basketballs in there. Ping pong balls. We can do whatever we want. And each of those, so here's my baseball. Okay, it's gonna have a number underneath it. And I have no idea what a dozen baseball weighs. I mean, I should know what a single baseball weighs, but I'm just gonna put X's there for the number. Okay, and then we're gonna have ping pong balls and what about soccer balls? I like soccer. I can't draw the octagons there. That's my soccer ball. Okay, and this is all the periodic table is. So the number underneath is the weight of 1 dozen of those balls. That's what it is. It's the weight of a dozen ping pong balls on my periodic table, a weight of a dozen baseballs, a weight of a dozen soccer balls. Okay, that's what that is up there. Only difference is that dozen is a little bit different than this dozen here. Okay, it also means it's also the weight of an individual one in a different unit. So that's what that is. That's the weight of hydrogen in AMUs of a single hydrogen atom, 1.00797. It's also the weight of a dozen. In my case, this dozen is Avogadro's number, 6.02 times 10 to the 23rd instead of 12. It's the weight of a chemist's dozen in grams. Okay? So what they're doing is using the same number. This is the beauty of the periodic table. It's all kind of built on comparison to each other in terms of weights. So you can look at that and say that carbon weighs about 12 times more than hydrogen does, the individual atoms, but also the dozen. Obviously, if a golf ball weighs 12 times more than a ping pong ball, then a dozen golf balls is going to weigh 12 times more than a dozen ping pong balls, right? That's all that is. Now, of course, we don't need to do this for a dozen because it's easy enough to count a dozen. It's easy enough to weigh a dozen. But when your number is 6.02 times 10 to the 23rd, and the reason this is done is because we can't count atoms. We can't even see an individual atom, let alone count, okay? We've got some, fancy computer images of individual atoms that are colorized and you can picture them, but we really can't manipulate and see something that small quite yet. So, and also you wouldn't have time to count them. I already demonstrated to you, it would take you like 10 years to count to 1 billion. And that's 10 to the 9. So we do this for convenience. So say I go into the lab and I've got a reaction, I'm running a chemical company, I've got a reaction, I want to react A with B. And I want to make sure that I use the right amounts of each. I don't want a bunch of stuff left over. They react in a certain proportion in chemical reactions. So how do I know that I'm putting enough there? I can't just use the same mass of each because that doesn't matter. If I'm reacting carbon with hydrogen to get methane, well, I can't use the same masses because we use 4 hydrogen for every one, and the masses of each of them are different, right? What I want to do is react them in the right numbers, right? I want 4 hydrogen or 2 hydrogen gas molecules for every 1 carbon. Well, I don't know the numbers. How do I know the numbers? Well, now I do. The periodic table allows me to say, okay, if I weigh out this much, if I weigh out 1 gram of hydrogen, that's hydrogen element, not the hydrogen gas, even though I showed this here. So you got to make that, commit that, recognize that. But we'll just do the carbon. If I weigh out to 12 grams of carbon, I have 6.02 times 10 to the 23rd. Maybe I don't want that many. Maybe I only want, 10 to the 9 carbon atoms. Well, then I can figure out how much mass I need, right? That's the whole point of the periodic table. Okay, so the mole is the SI unit for expressing quantities of substances. We call it Avogadro's constant. 6.022 times 10 to the 23rd is a mole's the number of atoms in exactly 12 grams of carbon 12. Carbon 12 specifically, because isotopes have different mass, and this is how the periodic table is structured. based on carbon-12 isotope. What we do is we figure out how many atoms were in carbon-12, 12 grams of carbon-12. We don't sit there and count them. There's different ways to do this, by the way. One way is X-ray crystallography. You can do this, and they've refined it over the years. Obviously, since Avogadro did this, you get more and more precise number for Avogadro. But the general idea is that it's based on the carbon-12 isotope. So that means that if everything's related, if the hydrogen is 1/12 in terms of the mass of a single atom, then that dozen is also 1/12. So all of this relates. So questions? So if you want 1 mole of silicon, all you have to do is weigh out 28.0855 grams, and you will have 1 mole, which is 6.02 times 10 to the 23rd atoms. So this is just dimensional analysis, then going back and forth. If you have numbers of particles, it's kind of like, I always tell my students, if you think about it like a dozen, it really does work. If I told you I had 36 eggs and asked you how many a dozen is that, all of you would answer that in a second, right? 36, you divide by 12. You divide by the number in a dozen. That's all you're doing here. You're going from numbers of particles, divide by the number in a dozen to figure out how many moles you have. If I told you I've got 3 dozen eggs, how many eggs is that? What would you do? You'd multiply it by 12, right? So now instead, just multiply it by 6.02 times 10 to the 23rd. That's all it is. It's like converting between eggs and dozen and eggs. It's no different. You're just changing the 12 to 6.02 times 10 to the 23rd. If you kind of think about that when you get stuck, might help you through. So let's try this. What time is it? Oh, it's early. A sample contains 2.59 times 10 to the 18 formula units. We're going to use formula units because it's not a compound. Sorry. Formula units of calcium chloride. How many moles of calcium chloride formula units are present? What do? Divide by Avogadro's number. Who said that? Andrew, right? Andrew says divide by Avogadro's number. That's all there is to it. 2.59 times 10 to the 18th units times 6.022 times 10 to the 23rd units in 1 mole. Now that units can be anything. It could be atoms, it could be ions, it could be formula units, it could be molecules, whatever you need it. Okay? Just like it can be eggs, ping pong balls, it could be whatever. And that's your answer. I don't know what the answer comes out to be. You have to do it. It's less than 1 mole, obviously. You see that. You're less than 10 to the 23rd, so it should be less than 1 mole. What do we get? 4 point what?
301.
We'll stop at O because we need 3 figures. 10 minus 6.
Yes.
Thank you. 4.30 times 10 minus 6 moles. We got a confirmation on that. That's all there is to it. Divide by, you're converting to dozens. Divide by your 12. Divide by your dozen. Questions? And you have another problem to practice. Start with moles and figure out the number of particles. And just multiply by 6.02. Now, molar mass is the mass in grams of 1 mole. I've already told you this. That's what's the beauty of the periodic table. It's the mass of 1 atom in AMUs or the mass of a mole in grams. So, gold's atomic mass is 196.97. And then, of course, its mass, its molar mass is 196.97 grams per mole, and SO2 is the same thing. So SO, you can take your molecular mass or your formula mass and make it a molar mass, or you can take an atomic mass and make it a molar mass. It's the same number, just change the units. Questions? If this type of thing helps you, then use it. I just put it up here for, something that's in the book and they provide. I just think about everything dimensional analysis and go through it logically, but this is basically what that's doing is, if you've got the mass and you want moles, divide by the molar mass. This is kind of what we just did, just laying it out for you in kind of a flow chart. This helps. All right, we're going to do a bunch of practice ones then. Mole calculations. How many moles of potassium atoms are present in 19.5 grams of potassium? What do we do here? Where did we get that number from? Your table selects potassium 39.0983. That's going to go in the denominator, right? Grams in 1 mole. Notice I took plenty of sig figs. I usually tell my students always take 1 more than what you're limited by, and your answer in the end will only be 3. And someone do that for us. What do we get? Anybody? For what? Thank you. Moles, notice our grams cancel out. You get moles. That's all there is to it. Yes.
So what would you divide by the atomic mass?
Okay, so it's not asking for numbers. It's funny you said that because I was about to say the students that get tripped up on these, they want to use sometimes Avogadro's number when they don't need it, or they want to use the molar mass when they don't need it. Okay, it's kind of like I said to you, well, this is a little bit tricky. This is the mass, right, that I have. And the molar mass is the weight of a dozen. It's kind of like saying, hey, I've got 50 grams of eggs and each dozen weighs 25 grams. How many dozen do I have? I have 50 grams divided by 25 grams per dozen, right? You don't need Avogadro's number. It's not asking for numbers of eggs. If you're asking for numbers of the particles, that's when Avogadro's number comes in. In this case, you just asked for basically how many dozen you have, and you're given the weight. Go to that periodic table of the balls I have. That's the weight of a dozen, right? If I told you I've got 50 grams of eggs, and I have no idea what a dozen eggs weighs, and a dozen eggs weighs 25 grams, that's what this question is. You've got the mass So you can take the periodic table, which is your mass per dozen, divide it, and now you know you've got basically about half a mole. And look at the numbers that make sense. It's about 40 and 20, right? You got about half a mole. A mole's about 40 grams, and you've got 20 grams. It's another way to think about it. Say, okay, that's the weight of a mole, 40 grams, and I've got 20 grams. If I said that all to you, right, you wouldn't even think twice about it. If I said to you, I've got a dozen that weighs 40, and you've got 20 grams, you all say to me in a second, I got half a dozen. That's all this question is. The second one. Was there any other questions on this one? Yeah.
Okay, so you're saying, Avogadro's number only, you want to know like the number of particles.
Right.
But
That's
you use the mass for what exactly?
well, right here. If you want to know how many moles, and you're given a mass. So here it is here. Let's see. You've got mass to moles. That's what we just did. Divide by the molar mass. Again, just like I say to you, if I said to you, if I've got 50 grams of eggs and a dozen eggs weighs 25 grams, how would you solve that? You would divide by the 25 grams to get 2 dozen. The second one, how many formula units, that's like saying numbers, are present in 5.3 moles of baking soda? That is baking soda, sodium bicarbonate. That's what we have, right? And we're asked for units or particles, if you will. Multiply by Avogadro's number. This is like saying I got 5.32 dozen. How many eggs do I have? We'd multiply by 12. 12 eggs per dozen. Well, instead of a dozen, replace it with 6.02 times 10 to the 23rd mole. Oops, particles per mole. In this case, it's what? Formula units. I'll just put units per mole. Your moles cancel out. You're left with units. You multiplied by Avogadro's number because you were asked for the number of particles. Dimensional analysis. If you look at Avogadro's number, the units are number of particles per mole. If you want moles, you're going to flip it, right? If you want particles, you're not going to, right? So this is the units. 6.02 times 10 to the 23rd formula units per mole. If you're trying to get moles, you're going to have to flip that. And that's what this is meant to show you here. So what do we get for an answer? And that's units, formula units. 3.20 times 10 to the 24th. And you can see that 6 times 5 is 30. It's basically 30 times 10 to the 23rd, which is 3 times 10 to the 24th. Questions? Yes.
So that was because it gives you the NHCO3. You weren't even need to like find the molar.
Yeah, that's what I've learned over the years. It's like for some students, you're having trouble seeing it. You see that formula and you want to add up all the masses, but it's not asking for a mass. And again, you're told anytime you see the word moles, replace it with dozen. And you're asked for how many formula units. Let's just think about the number of particles. If you're given the dozen, and you ask for number of particles, why do you care about the mass of an egg? Right? We're just asked for how many eggs there are. Other questions? Oh, I had it solved like that. Doesn't matter, we did it, so. There's the 0.499. .2 to 1024. Very good. All right. How many moles are present in 58.4 grams of chalk? I've given you the molar mass, we have to take time to add it up, but normally you would have to say calcium plus carbon plus 3 oxygen, and it's right around 100 for chalk. Calcium carbonate. I've got 58.4 grams. Asking for moles. Do I need Avogadro's number? No, not asking for particles. So all it is, once again, 100.09 grams per mole. Cross that out. You've got your answer. I don't know if I solved this one. I didn't. Moles. We should have 3 sig figs, but that's all right. 0.58. Is it 0? 3? Now, if I was asked for number of particles, I can do the next step. 0.583 moles times 6.02 times 10 to the 23rd per mole. And that would be, this is be particles again. I like to use particles because I can use that for everything. Whether it's an ion, a formula unit, a molecule, you say particles. That would be the step we used for the numbers of particles if you were asked for Avogadro or asked for numbers. So you'd set it up to do just 2 steps. That's all. Looking at your units again, dimensional analysis, gets rid of the moles, I'm left with particles. That's the power of dimensional analysis. It'll keep you, if you carry your units through, it'll keep you from making a mistake. Questions? So you got this weekend to practice your mole calculations. Here's one that adds another dimension. The uranium used in nuclear fuel exists in nature in several minerals. Calculate how many moles of uranium are found in 100 grams of carnotite. And there's the formula for carnotite. I didn't want to take up the time to add all that up, so I've given you the mass. This is what we call a hydrate. That dot with the 3 H2Os, that's just water associated with the crystal. You have to add that up like any formula mass. Okay? So when you add a dish, you'd have to do 2 potassium, 2 uranium, 2 vanadium, and then we got what? 8 and 4, 12 oxygen there, and another 3 oxygen there, and 6 hydrogen. You have to add all this up. It's good practice. You should do it at home. And you get 902.19 grams per mole. Did I solve this one? I forget. No, I didn't. Okay. So, perfect timing. Okay. We've got 100 grams. What do I do? What's that? Divide by what, Megan? Very good. So Megan says, let's divide by this 902.19 grams per mole. Why? Well, it gets rid of the grams and we got moles. Let's see what the question asks. Uranium used in nuclear fuel exists in nature, several minerals. How many moles of uranium are found in 100 grams of carnotite? Am I done? No, you're shaking your head. No, John. John, why? Right, that's moles of carnotite. Right? That's the molar mass of car, and that's moles of car, right? We got rid of grams of car. We now have moles of carnotite, but the question is asking for uranium. How many moles of uranium? So we can say 2 moles of uranium for every 1 mole of car. And so we actually have twice as many because that's a subset of it, if you will, right? Of the mineral. So the moles of Car are gone. We now have moles of uranium. So when it asks for a specific atom in a formula, look at the number, right? And then multiply it by that. If it had asked for potassium, it would be 2. Vanadium, it would be 2. Hydrogen, it would be 6. Oxygen, what did we say, 12? No, 12 and 3. 15 oxygens, right? So what do we get for an answer there? Anybody do it? .0. And that is what? Moles of uranium. And 4 sig figs, we're good. We got 4 with the 100 grams, so that's good. 0.2220 moles of uranium.
It should be 0.22.
2217. Okay. Yeah. It's multiple choice. We got it right. Yeah. Right here. There's a 2 here and you're outside the parentheses, so that means there's 2 uranium. So it's almost like you got like subsets, right? You got this mineral, but you got 2 uranium in that mineral, and you got 2 potassium. So that's why we need this last step. Because
The chloride is that whole.
yes,
Okay.
that's that whole mineral. That's right. Carnotite's that whole mineral, and it's asking specifically the number of uranium atoms, if you will. Or actually, it's not asking the number of atoms, it's asking the number of moles. If we wanted atoms, then you can do the next step. Go ahead and multiply it by Avogadro's number. Questions? I'm exhausted. I slept like crap last night. We good? There's our summary for chapter 2. So we have all of Tuesday to just work mole problems to death if you want. Make sure you understand the major contributions from these scientific experiments from this chapter. The nuclide stuff when describing, these different nuclides of particles, charges and protons and neutrons. Periodic table and different properties of the elements. And then the last 2 are the big calculation parts. When you see isotopic abundance calculation, you'll have 1 calculation on the exam of that. Moles will probably have like 3 or 4, but there'll only be 1 isotopic abundance calculation. There might be another question, like I did the qualitative one, where I say, hey, here's isotope, which one's the major, that type of thing. Okay? Have a good weekend. Enjoy the weather. I think it's supposed to be nice, right?